All right, so these notes are going to focus on quantifying work, and I want to just let's look at this one situation. Here you are, and you're getting ready to push on a cart. When I say go, not yet, but we see that the cart isn't moving, and then I look at you sometime later, and I see you're standing there, and the cart is moving, and I want to know a couple of things. First, let me delete those arrows. I want to know two things. I want to know, did you do work on the cart? And how much work did you do on the cart? Well, I think the answer to the first question is, hopefully you'll see, is pretty obviously yes, because the cart has kinetic energy after you're done with your push, and here at the beginning the cart had no energy, and so the cart has energy at the end. It didn't have it at the beginning. Energy has to come from somewhere, and I'm pretty sure it came from you. All right, the next question is a little trickier though. Is how much work did you do on the cart? And that's going to be the topic for today. And there's really two ways to think about that, or there's two ways to get to the answer of how much work did you do on the cart. The first way is what we have already talked about, is this idea of the work energy theorem. I don't know who comes up with these ideas, but there's this idea of there's a relationship between the work you do on something and the energy it has. And let's just suppose at the end of your push, you just happen to know that this thing had 300 joules of kinetic energy due to its motion. And here at the beginning, it had 0 joules. How much work did you do? Well, the work energy theorem tells us that the work you do is equal to the change in energy of the system upon which you did the work. And so in this case, you would clearly know that you did 300 joules of work. You don't need to know the force with which you pushed the cart. You don't need to know the distance through which you exerted that force. You absolutely know the amount of energy transferred because you know, well, the amount of work you did because you know the amount of energy that was transferred. That's not really our focus for today. Our focus for today is this idea of, all right, I feel like doing that. All right, the focus for today is, what if you don't know how much energy? What if this information isn't available to you? What if you don't know that? Is there another way that you can know the work done, the work that you did? And the answer is absolutely, because there's a definition for what work is. So this is what work does. Work transfers energy, but how do we define how much work was done without, not without thinking about the amount of energy, just based on force and distance? Well, here it is. This is our focus for this little video notes is, and this is for a constant force, by the way. So if you have a constant force, how do we define the amount of work you do, independent of the energy transfer? All right, the work you do is going to be equal to the size of your force. Well, it's okay, your force vector dot the distance vector. And that is, what does that mean? What is, how do you, all right, well, that's our topic for today. Okay, so we're going to look at how do we use this definition of work to figure out how much work is done. So here I have on the left, I've got our definition of work. And on the right, I've got an example. And I think it's the best, well, that's what we're going to do. We're going to go through this example right here. So this is our example. And let's just give you some context. Suppose that this is like a suitcase. This guy right here is a suitcase, and it's got these really nice wheels, so it rolls with no friction. Friction is negligible. You're pulling with 20 newtons of force. That's like 4 or 5 pounds. But and you're pulling it at 30 degrees above the horizontal, and you pull it through a distance of 5 meters. And the question is, how much work did you do? Well, let's see. Let's try this and see if it's wrong or right, because it's going to be wrong. All right, so here you go. I'm going to take my, I don't like that. Too thick. I'm going to say that work equals, okay, what was the force? 20 newtons. And this is, I've seen that before, that's multiplication. And so I'm going to take 5 meters, and this is wrong, by the way. And, oops, sorry. You're going to get 100 Newton meters. Now, this is wrong, but not everything in here is wrong, okay? The thing that's right are the units are correct. And hopefully in the reading or in the notes or somewhere, you know that, oh, a Newton meter has been defined as a joule in honor of James Prescott Joule, who did a lot of work on this energy stuff. So I like the fact that the units work out. I also like the fact that we have discovered that work is a scalar, meaning not a vector. So that part I like. So this is different from like torque. Torque, we multiply two vectors, a force vector and essentially a moment arm vector, that R vector, and we ended up with a vector quantity. Torque is very much a vector quantity. It has a direction. Here, work also involves the multiplication of two vectors, but it's a scalar. There is no directional aspect to energy. All right, now what's wrong? Let's get to what's wrong. The wrong part is that we took the magnitude of the force and we multiplied it by the magnitude of the distance moved. Sometimes that's okay, but in this case, that's wrong. And the reason it's wrong is because your force wasn't perfectly parallel. It wasn't perfectly in line with the distance vector. So let's talk about how to deal with that in the correct way. We are now going to do it the right way. All right, so I have it here. This is the same setup again, and let's do it the correct way. All right, I'm going to write it first out in words, which is going to be way too many words, and then we're going to do it in symbols. Okay, so work is equal to, let's say, okay, I'm thinking of the component. I'll do component of force in direction of motion. That's all. I think times the amount of, no, not the direction of motion, the distance moved. Okay, so let's take this essentially is in words is how we define work. Okay, if you want to quantify work, figure out how much distance was involved. Something moved 5 meters, 10 meters, whatever. And then here's the little bit tricky part is you have to figure out, okay, how much of the force, what component of the force was actually in the direction of the motion? And that's essentially is what this kind of weird looking formula is. So this is called the dot product. We're not going to spend too much time. In fact, we're going to spend almost no time calling it the dot product, but that's how work is formally defined. So how is it used practically speaking then? Okay, well, let's do in this example. Okay, so work is going to be only the part of the force that's in the direction of motion times the distance moved. Okay, well, here is, let's just draw it and see why. Okay, so this is going to be F cosine theta times the distance moved. Okay, why is it F cosine theta? Let's look at our force vector. I'm just drawing the same, well, this guy represents that force. And I'm going to basically put my distance vector tail to tail. And so this is my distance moved vector. And this guy is the force vector. And you only get credit. So it's only the part of the force that's in the direction of motion that does work. Okay, I'm going to end this. This is the end of part 1 because I got interrupted by something and I have no idea where I was. So I'll watch this video and then we'll start part 2 as we go through this problem. Okay, move on to part 2.